I'm Mark Chen. I'm a professor at Queen's University, and my research field is particle astrophysics. So what I'm interested in is I study the fundamental properties of the smallest constituents of matter. Why do I do this? It's because the interactions of particles and their properties affect the evolution of the universe. And one of the things that we do in our field is that we study the cosmos by building giant particle detectors, and we go deep underground and install our detectors underground in order to study the universe. So a very unusual thing to do. Normally when you think about studying the cosmos, you want to look up, but we go deep underground. We go 6,800 feet underground in Sudbury, exactly. So let me start with this image, which shows the composition of the universe in a pie chart. This is a remarkable image, and actually the contributions from the CIFAR Cosmology and Gravity program and a lot of the work from the members in this program gave us the information that allows us to understand the composition, the matter, energy, density components of the universe. And there's this large chunk, the dark energy, that we really don't know that much about. And there's a fairly large chunk, the dark matter, that we have some ideas about. And then that's the component that we're going to try to go after with our particle detectors in Sudbury. So this image provides very strong evidence that dark matter is not the same as the ordinary matter that make up atoms, make up stars, make up you and me. I'm going to try to explain the evidence that dark matter is a different type of particle from this image, and we'll see how it goes. The image is actually is a superposition of three different images. There is the optical image from telescopes, so you see galaxies, all sorts of galaxies in the image, telescopes like the Hubble Space Telescope. In red, we see an X-ray telescope map of the X-ray intensity. What we see here, this is called the bullet cluster, and there are two galaxy clusters that we can tell from the observations have passed through each other. And this one in particular is moving very fast through this other galaxy, and so this has happened millions and millions of years ago. But what we see today is that in passing through each other, there is gas that's been heated up from friction and has been slowed down from drag, and that hot gas emits X-rays, and X-ray telescopes can show us where that matter is. And in fact, we even see what looks very much like a bow shock in this image from the X-ray. And in blue is a map of the dark matter. This is a mapping that's done with lensing, with weak lensing. And you heard this morning from Gil Holder explaining how by looking at the shapes of galaxies in the background and the distortion of the light as it passes through large concentrations of matter, meaning these two clusters of galaxies, how the distortions of those shapes allow us to determine the location of the matter in this image. And they're in the blue. And so what one sees from this image is that the blue and the red are very separated, right? It's as though the blue stuff passed through each other without interacting, whereas the red stuff, the ordinary gas, the hot gas, has experienced interactions that has heated it up. And so that image alone, but there's a whole host of other observations, astrophysical observations, that have given us the following picture of what dark matter is. And so I'll run through what we think dark matter is. Dark matter we think is what we call non-baryonic. That means it's not like ordinary matter. It's not made of protons and neutrons and electrons. It's got to be something else, some other type of particle. Then the dark matter is weakly interacting. We say collisionless sometimes, but it's possible that dark matter has a weak interaction, and so then that may give us an opportunity to try to detect dark matter particles directly. Dark matter is cold. That means it's made up of non-relativistic particles. Our models in cosmology tell us this. And dark matter clumps together due to gravity, and it's the presence of dark matter that actually provides a seed for the ordinary matter to clump and form the large-scale structure that we observe in the universe. So physicists, we don't know, so that's what we know about dark matter. So what physicists don't know is exactly what kind of particles form the dark matter that pervades the universe. And there's several leading ideas that dark matter could be these particles we call WIMPs, these weakly interacting massive particles. It could be excitation states of extra space-time dimensions. They could be these particles we call axions. What we want to do is we want to try to detect these particles directly and thereby determine what dark matter is. But there are a lot of ideas that are out there. So here's a simplified overview of, of all the ideas that are there. So particle theory has dreamed up lots of different ideas for dark matter, and how they're related to each other. I love this image. But the key thing is that if dark matter is a weakly interacting particle, then we have a chance to detect it. And so we're going to mount a program to try to directly detect dark matter particles in a large particle detector, and we have to do that underground. All right, so we are passing through a halo of dark matter. We heard about that this morning from other speakers. So the Earth is moving around the sun is moving through the galaxy, and so the galaxy is passing through this cloud of dark matter that is surrounding all of the galaxies. That's our understanding. And so we're actually experiencing this wind of dark matter that we're passing through. And the dark matter, being very penetrating and virtually collisionless, is passing right through us and all the way through the Earth. And in the most part, the dark matter doesn't experience any interaction with the ordinary matter. In contrast, though, there's a continuous rain of cosmic rays, particles that are with a flux that are millions of times more intense than the flux of the particles from dark matter. So we have to go deep underground in order to be shielded from the cosmic radiation that would otherwise blind our detectors from seeing these very, very rare interactions. And so this is an illustration, an artist's illustration of these cosmic ray particles generated from energetic particles that are coming from the cosmos. As they strike the atmosphere, they make a rain of these particles. And so we go deep underground, and then the rock and Earth that will be above us will provide the shielding to screen out these particles. So only the most penetrating of particles will make it to our detectors. So literally, we go deep underground and we carve our experiment out of rock. And so this is a picture of the excavations that took place in the Valley Creighton mine near Sudbury, Ontario. That we really dug this space out of rock, these giant caverns underground, and then transformed this into an ultra-low background, very clean facility to allow us to install very sensitive particle detectors to search for dark matter particles and neutrinos. So this enterprise that's underground in Sudbury is called Snow Lab. This is a map of the terrain at the 6,800-foot level in the mine. Snow Lab is in the Valley Creighton mine. It's an active mine. And so we descend underground, actually around here, and then we have this, to give you the scale, this is about 1.6 kilometers. So it's about a 1 mile walk underground from where we get off on the elevator before we enter the lab. And Snow Lab is the descendant of the Sudbury Neutrino Observatory. And the Sudbury Neutrino Observatory, SNO is just this portion here, and the lab is the expansion with new space. And this is a map, right? So you're seeing it tilted, right, to give you the perspective of the map. Although we're underground, it's not as though this is at a shallower depth than this location here. So let me take a quick diversion to tell people what the Sudbury Neutrino Observatory was. It was a giant neutrino detector, so I'll just spend a few minutes talking about neutrinos, where we detected neutrinos produced from the sun. This is a sphere. You can see a person here for scale. This sphere is 16 meters in diameter. Each one of these nodes is a very sensitive light detector, so 10,000 light detectors surrounding central volume. So if you stick a fisheye lens into that sphere, you see now a 12-meter diameter acrylic ball that we filled with heavy water in order to detect neutrinos. Neutrinos being a fundamental particle, also very weakly interacting. And so it was this activity that got the Nobel Prize for that project leader, Art McDonald, the 2015 Nobel Prize in Physics. Art and the SNO collaboration that I worked on, we discovered that neutrinos, they change from one type to another. And that observation is really important. It teaches us that neutrinos have a finite mass, and the role that neutrinos play in the evolution of the universe is being unraveled with this new information. To wrap up my discussion about neutrinos, let me just tell you a little bit about what's happening with the SNO neutrino detector. We had the pleasure of Stephen Hawking's visit 5 years ago, and I'm showing this image to show you what it's like to work underground. We go underground dressed like miners, but when we enter the lab, we shower, we clean, and we dress in clean room clothes in order to keep the lab space clean and free from trace contaminants. And this activity, installing a very large, clean lab deep underground in a mine, you can imagine how all the measures that are required in order to pull that off. And the neutrino detector, this is the project that I lead. We're refurbishing it. We're putting the last polishing touches on the refurbished neutrino detector. It has turned back on this year, and we'll soon be reporting new data and detecting neutrinos. But getting it back then to conclude about dark matter, we have also built in SNOLAB the world's largest dark matter detector. And so that's a remarkable thing to say that thing is in Canada. This project, this experiment is called Deep 3600s because it currently is filled with 3.6 tons, 3,600 kilograms of liquid argon. Argon being the noble gas. It's liquefied at a temperature of minus 190 degrees Celsius, and it serves as an ideal detector for looking at the signals of dark matter. This thing is running, and we're doing our search right now to see if dark matter particles are interacting under a detector. That's what it looks like. A sphere which gets cooled down to liquid argon temperatures. Each of these nodes is one of those sensitive light detectors, and the entire thing enclosed in this steel shell and then filled and placed in a water tank. And so to conclude, I'll bring it back to this picture, the pie chart composition of the universe. So we have this as one of the biggest questions in astrophysics and cosmology, is to really understand the dark universe. What is this component, and what is this component, the dark matter? And there's a major program underway in the world to try to identify what this dark matter is, and one of the leading programs in the world doing that is right here in Canada, and this is our share of the pie right there. That's what we're going for. Thanks very much.